Good morning, everybody. So on Friday, we started talking about how we can use optimization as a tool to control robotic systems. In particular, we saw that there is this special kind of optimization problem called a quadratic program, where we have a quadratic cost function and linear equality and inequality constraints that we can use to generalize the control techniques that we have seen the previous times. In particular, we have seen how we can generalize joint space inverse dynamics. And the generalization mainly consists in adding inequality constraints to the problem. These inequality constraints we can use to represent the motor torque limits, the joint velocity limits, the motor current limits. Yeah, there is this noise. That's going to be a challenge. Is it less loud? No. Okay. So it doesn't depend on the volume. Okay, I think we're going to have to live with that. To a certain extent, you could also account for joint position limits, but I've shown you how that's a bit, but it stopped. That's a bit more challenging because you have this problem of having to basically decide when it's time to start decelerating in order to avoid hitting the joint position limit. And these kind of tools we are dealing with right now, the so-called reactive control methods, are not really the right tools for addressing those inequalities. Later in the class, we'll see other tools which are more powerful that you can use to address joint position limits or in general obstacle avoidance constraints. So after dealing with joint space control, we also saw that we can generalize this to Cartesian space control. And this is the optimization problem we ended up formulating, which is very similar to the one we saw for joint space. The only difference is the cost function. Now the cost function measures the error in the acceleration in Cartesian space instead of joint space. So it's a very little change. The overall problem remains the same. And here I'm not showing, but you can, of course, add the inequality constraints we were discussing about a moment ago. And at the very last part of the lecture, we started discussing how to generalize from Cartesian space to task space, where a task can be any control objective that you want to assign to the robot. And so we started working on this more like a general formulation where we define an error function, which is some function of state and control and time, which actually we restrict to taking this form here. So a difference between a reference value, which depends only on time, and our, let's say, real value, which depends on state and control. And we saw that this could be many things. It could be the orientation of the camera of the robot. It could be the position of a foot of the robot. It could be the center of mass of the robot. It could be the angular momentum of the robot. It could be the joint torques. Any quantity, any nonlinear function of state and control can be plugged in here. And then how do you transform this into something that you can use inside your quadratic program? Because you cannot directly use this in the quadratic program because this depends on the state, which is Q and Q dot. And the decision variables of your quadratic program are Q double dot and tau. So there is a mismatch there. So the idea that we said we were going to exploit is to try to work on the dynamics of the error. So it's going to be either the first derivative or the second derivative, depending on the case. And then we're going to impose the dynamics of the error such that the error goes to zero as time goes to infinity, which is what we want. We want to achieve zero error. And we need to make sure that the dynamics is an affine function of my decision variables of the problem, because otherwise it's not going to be a quadratic program anymore. I want to maintain a quadratic program. So I think we stopped here. We derived the case for the velocity task function. So that's a special case where the error is not a general function of the whole state and control vectors, but it's only a function of the joint velocities, q dot. So in that case, this is a derivation. We saw that the error, basically, the first derivative of the error can be expressed as a linear function of q double dot, which is what I wanted, because q double dot is my decision variable. And then here I could impose any dynamics I wanted. It doesn't need to be linear, but it happens that the linear dynamics is good enough for most practical cases. And so we simply decided to set E dot equal minus KE. Why this doesn't need to be linear, whereas this needs to be linear? Did you get that?
Can you repeat that?
Why this expression here needs to be linear in Q double in the decision variables? Whereas this expression here, I told you, you could impose the dynamics as any nonlinear function of E.
Because it must be linear with respect of Q double dot and tau. So the error is not function of Q double dot and tau. So
yeah. So basically, the error is a constant when you solve the problem. So here you can have any nonlinear function of the error. It doesn't matter. It's going to remain a constant. What matters is if you're linear or not with respect to the decision variables of the problem. With respect to other quantities that you have in the problem, which are constant, you can have any nonlinearity that you want. So here, if you want to plug in, I don't know, the tangent of E, you could do that. Or if you wanted to take the error to the power of 3, you could do that. It doesn't matter. I mean, of course, you need to make sure that this dynamics converges to 0, because that's what you really care about. But it doesn't necessarily need to be a linear dynamics. But linear dynamics, again, are good enough for most practical cases, so we're going to stick to that. In the end, we managed to express everything as a linear function of Q double dot. And then we said that instead of plugging this as a constraint in my optimization problem, it's much smarter to use it as a cost function, because in case the equation is not feasible, so it doesn't admit an exact solution, if you have it as a constraint, you end up with an unfeasible optimization problem and you're in trouble. If you just plug it as a cost function, it's fine. It's just going to try its best to satisfy that equation. And I think we stopped here. Now we're going to do exactly the same derivation for the other two cases, which are the most common in practice. So now we saw the case where the task is a function of velocities. Next, we're going to see the case where the task is a function of positions, so the joint angles, Q. And finally, we're going to see the case where the task is a function of the control inputs, U. So the case where the task function depends on the joint configuration is actually very similar to the one we just saw for the velocities, with one crucial difference. Since before we started with velocities and we wanted to get to accelerations, we just needed to derive the equation once. Now we start with positions and we want to get to acceleration, so we need to take the derivative twice. That's the only difference there. So our error function, we said, is going to be a function only of Q and time. We don't have any dependencies on Q dots and U. So we can write it as some reference, some quantity y of q minus some reference yr of t. The reference can be time varying. It can also be a constant, of course. Okay, so that's my definition of the error. So if I take the first derivative, I get y dot minus y dot r. And now I want to express y dot as a function of the variation of the joint angles. So I use the chain rule as I did last time to express this as a derivative of y with respect to q times the derivative of q with respect to time. The derivative of y with respect to q is a Jacobian matrix because I'm deriving a quantity which is multi-input, multi-output. And so I get a Jacobian. So in case this quantity y here is the position of my end effector, well, this Jacobian is exactly the Jacobian that we saw in the previous lectures. But in general, it's going to be a different Jacobian. It's going to be a Jacobian that describes the derivative of this quantity with respect to the joint angles. And this quantity here, well, that's just the joint velocities, because you're deriving with respect to time the joint angle, so you get the joint velocities. So jq dot minus y dot r. At this point, we realize that we cannot stop because we don't have, again, a function. We don't have yet a function of the joint accelerations. We only have a function of the joint velocities, which are not a variable of my problem. So I need to take the derivative one more time. This time is pretty simple. If I take the derivative of this, I get this expression. Because here I have the derivative of a product. So I apply the usual rule. The first term times the derivative of the second term plus the derivative of the first term times the second term, which is missing a dot clearly here. And the derivative of the reference, well, that's simply y double dot r. And now I'm satisfied because I have an expression which is a function of q double dot, and it's a linear function of q double dot. So that's exactly what I was hoping to get. And now I need to do the same thing I did before. So I need to decide what kind of dynamics I want to impose for this e double dot. And again, this could be any nonlinear function of e and e dot, but a linear function happens to work just fine in most cases. So I'm going to impose a linear dynamics. So e double dot is equal to minus kpe minus kd e dot, where kp and kd are going to be user-defined gains, which need to be positive definite. And if these are positive definite, actually we have already analyzed the stability of this dynamical system. We saw that as long as the gains are positive definite, this dynamical system is stable. So it's going to converge to zero as time goes to infinity. Then if I take this expression and I substitute it in here as my desired value for e double dot, I get this equality. And then I just move things around so that I have everything that is constant on the right-hand side. So this term here is constant. I can move it on the right-hand side. And my final expression, as usual, is a linear expression of q double dot, which is going to be inserted in the problem as a cost function for the same reason we discussed before. So the main difference in practice is that when you have a task function which depends on the joint configurations, well, you're going to end up having two feedback gains to tune, because you're going to have a proportional gain and a derivative gain. If instead your task function depended only on velocities, you're going to have only one feedback gain, which is going to be acting on the velocities. You're not going to have any feedback on the positions. That's the most practical difference between these two cases. But apart from that, they feel pretty similar. So we saw the case of a position task, of a velocity task. What we are missing is a case where your task depends on the control inputs. So that's very often the case where you want to just minimize the control inputs, and it's typically a secondary task. It's not your main objective. Now, this one is going to be very simple and different from the other two we have seen, because the control inputs happen to be a part of your decision variables. So in this case, we don't need to do any derivation, any dynamics analysis, because you already have a function that depends on your decision variables. However, here we're going to be much more limited, because we know that our optimization problem is a QP, so we can only afford to have quadratic cost functions and linear constraints. So it means that this error function must be affine in my control inputs. So it must be a function that takes this form. Here I cannot have a nonlinear function of u. Okay, because my QP doesn't allow me to have a nonlinear function of q. So the function must be already linear. In practice, this is not a problem, because typically the way you're going to use this most of the times is going to be having a term like that in your cost, or something like that. So maybe you want to minimize the control inputs, or you want to maintain the control input as close as possible to some reference value, which are typically the control inputs that are needed for compensating gravity in a given configuration of the robot. So these are already linear functions, so you don't need to do anything actually to use them. Maybe you could insert some weight. Where W is a diagonal matrix where each element of the diagonal corresponds to the weight that you want to assign to the minimization of the torque at that specific joint. That's in practice useful, because typically your robot doesn't have all joints with the same motors. So at some joints you have motors that are much more powerful than at other joints. So it makes sense to assign a higher weight to joints that have a bigger motor, basically, so that they can apply more torque. Mm-hmm. And all of these are linear functions that end up giving you a quadratic cost. So we have covered the three cases. Let me recap what we have seen. We can have three kinds of task functions. You can either have directly an affine function of the control inputs, which are the joint torques. And in that case, you don't have to do anything. Or you could have a nonlinear function of the state, which most of the times it's either a function of the joint velocities q dot, and in that case you just need to take the derivative of the error once and impose a dynamics for this derivative. Or if it's only a function of q, then you need to take the derivative twice and impose the dynamics for e double dot. But in the end, no matter in which case you are, what you end up with is an affine function of the decision variables. So you end up with something like this. So you get a matrix A, which multiplies your decision variables vector Z, which contains q double dot and tau, minus some constant B. In all three cases, what you ended up with can be written in this form. So from now on, in the next slides, I'm always gonna work with this like general form of the cost function. And then of course, when you plug this into your problem, it's gonna be in this way, because it is the linear function that goes inside the squared norm, which you use as a cost function, which is going to make your cost function quadratic and convex, because it is a least square program, which is a special kind of a convex quadratic program. Now, so far we have only discussed how we can use this optimization-based framework for controlling robot manipulators. But actually, one of the advantages of switching to optimization-based control is not only that you can add inequality constraints. I think that's the main advantage yet still, but there are other advantages. And one important one is that you can deal with other kind of robotic system beyond robot manipulators. Okay, this is another recap slide. So I'm just basically summarizing everything that we have seen so far in this one slide before adding new material. So this is a very compact way of rewriting the task space inverse dynamics problem. I introduce this new notation Z, which represents the stacking of my two decision variables, q double dot and tau. Then my cost function is going to be a generic least square function of my decision variable. And my constraints are simply the dynamics, which I can write in this form. It's just a matrix form. So I have M, which multiplies q double dot, minus the identity matrix, which multiplies tau, equal to minus H. And if you just move tau on the right-hand side and H on the left-hand side, you recover the usual expression M q double dot plus H equal to tau. I wrote it in this form, not just because I enjoy making your life harder. It's just that when you give this equation to a solver, the solver needs this equation in this form, because it's going to require you to specify the matrix that pre-multiplies the decision variable and the offset, the constant offset. So this is the form that the solver wants. And now below I specified the values that A and B take for the two special cases we started with. So in case you want to do joint space control, then the matrix A is simply going to be an identity matrix and next to a zero matrix, where the identity matrix is the one that multiplies q double dot, and the zero matrix is the one that multiplies tau, so that when you multiply A times Z times Z, you get Q double dot. And the B vector is simply going to be Q double dot desired. So when you do the multiplication AZ minus B, you get Q double dot minus Q double dot desired. In the case, instead you're doing Cartesian control of the end effector, the matrix A is going to be the Jacobian matrix on the left and the zero matrix on the right, so that when you multiply A times Z, you get JQ double dot. And the vector B is going to be X double dot desired minus J dot Q dot. So that when you do the whole multiplication AZ minus B, you get JQ double dot plus J dot Q dot minus X double dot desired, which was the cost function that we had for doing Cartesian space control. No, it was worth a try. I broke it. I seriously broke it. Okay, end of summary. Let's move on to different kinds of systems. So robot manipulators are a special kind of robotic system because they are fully actuated systems. What does it mean that they are fully actuated? It means that at every joint, at every degree of freedom, you have a motor that actuates that joint. That's what fully actuated means. But there are many systems that are not fully actuated. Some of them are underactuated, others are overactuated. So overactuated, it means that you have more actuators than degrees of freedom. Underactuated, it means you have less actuators than degrees of freedom. Actually, most robotic systems, especially mobile robotic systems, are underactuated. That's much more common than overactuation. It's more convenient to have an underactuated system because it means you have less motors, less sensors, it costs less, it's simpler to manufacture. I mean, it's more convenient in a very broad sense. So just to give you a few examples before entering into the math, legged robots, they're all underactuated. Flying robots, they're all underactuated. Well, not all, but most of them. Like take the quadcopter. How many degrees of freedom a quadcopter has? 6 degrees of freedom because it can move in free space. It's a rigid body, basically, which moves in free space. So 3 for position and 3 for orientation. How many actuators does a quadcopter have? 4. It's a quadcopter because it has 4 propellers. So it's underactuated because 4 is less than 6. Underwater robots, I'm not an expert, but most of them are underactuated. I couldn't tell you exactly how many actuators they have, but for sure they have less than 6. And they have 6 degrees of freedom, of course, because like a quadcopter, they are a rigid body moving in 3D space. Wheeled robots, take your car, for instance. How many degrees of freedom does your car have? 3, because it doesn't fly unless you make it, but that's not supposed to happen. So you can move in X and Y on the plane, and it has orientation. So 3 degrees of freedom. How many actuators does it have? Two, because you can turn the wheels, and that's 1 degree of actuation, and you can accelerate and brake, and that's another degree of actuation. So 2 actuators, 3 degrees of freedom, it's underactuated. Legged robots, I kept it last because it's a bit more convoluted. How many degrees of freedom a legged robot have? So suppose, of course, there are all the joints, because you can think of a legged robot as taking like 4 manipulators and attaching it to a body, which is the trunk of the robot. So you're going to have all the degrees of freedom of the 4 manipulators, 2 for the arms, 2 for the legs. But is that it? No, because it can also move in space, contrary to the manipulator, which is typically fixed to the ground or to a table. So you have all the degrees of freedom of the joints, which are n, an arbitrary number n, plus you have the degrees of freedom coming from the fact that this robot can move in 3D space, like the quadcopter or like the underwater robot. So that's going to be another 6. So a legged robot has n plus 6 degrees of freedom. And how many motors or actuators does it have? N. So n is smaller than n plus 6. So it is underactuated. Can we imagine making it fully actuated? What would you have to do to make it fully actuated? No, it's the other way around. You need to add some actuators. Can you imagine what kind of actuators would you need to add? Wheels could help a little bit, but not enough. What about Iron Man? Is Iron Man underactuated? It can fly, which is cool. But is it underactuated? It's still underactuated, but less so, because it has 4 propellers at the end effectors, right? At the feet and the hand. So you add basically 4 actuators. So it's n plus 4 actuators and n plus 6 the degrees of freedom. It's still underactuated, but it's almost fully actuated. You would need to add another 2 propellers somewhere, and you could make it fully actuated. Okay. Of course, it doesn't exist in practice, this robot, but actually they are trying to make one in Genova since a decade. They're working on it, but it doesn't fly very well yet. Okay, so long story short, most mobile robots are underactuated. So it's very important if you have a controller that is able to deal with underactuated system, because there are many of them. Before we talk about how we control an underactuated system, we need to discuss how we model an underactuated system. It's very simple. It's a minor change with respect to what we have seen so far. So let's start with a very simple underactuated system. We take a robot manipulator and we remove 1 motor. It's underactuated, okay? Because you have 1 motor less than you would need to make it fully actuated. How does this affect the dynamics? Well, it's actually quite simple. You take the vector of the joint torques, it contains the joint torques for every joint. If you remove the first motor, the effect is that the torque at the first joint is always going to be 0. So you're simply going to have a 0 as a first element in that vector. So we can rewrite the dynamics in this way. We are simply adding this matrix S transpose in front of the joint torque vector, where S is basically a selection matrix which contains only zeros and ones. And actually it contains zeros in the columns corresponding to the passive joints and ones in the columns corresponding to the actuated joints. So in this case, it would be the first column, it would be a 0, and then all the other columns would have a 1. So when you multiply S transpose times the new vector, which contains all the joint torques except the first one, you get a vector which has the right size and contains zeros in the rows corresponding to the passive joints. It's a very little change. You're just adding this selection matrix in front of tau. And with this, you can model all these robots that we have discussed about below. So legged robots, flying robots, underwater robots, wheeled robots. You just add the proper selection matrix in front of tau, and you get a model that works for all those robots. Because underactuation is basically just that. You remove some torque at some degrees of freedom. It's nothing more. Okay, so now that we have a model for all underactuated systems, we can think of how do we use this model in our control framework using quadratic programs. It's surprisingly simple. This was your optimization problem before, and the only thing that you need to do is you need to replace here the identity matrix with this new matrix S transpose. So when you do the multiplication, you have M minus S transpose. So these are two parts of the matrix times Q double dot tau equal minus H. You do the multiplication, you get MQ double dot minus S transpose tau equal minus H. And then you can move things around and you get the usual form MQ double dot plus H equal S transpose tau. It's extremely simple. You just replaced one matrix with another one. But apart from that, the overall framework remains exactly the same. So everything we were doing before for fully actuated systems, we can still do it for the underactuated systems. And that's super powerful because if instead of using this optimization-based controller, we were using the classic control techniques that we discussed before, like operational space inverse dynamics, or well, all the other control methods for joint space control we have seen, it wouldn't be that simple to introduce underactuation, because we will need to redo all the math for deriving the closed form expressions of the controllers. Here, we are relying on the solver to do the math for us, which makes our life much, much easier. Basically, we can focus much more on the modeling and not on the solving. Once we have the model, the solving, well, the solver does it. That's his job. Okay. Question on this? We can keep extending. So another very useful feature of these QP-based control methods is that they can also deal with contacts. So far, we have only discussed the case where the robot is not making contact with the environment, but in practice, most robots need to make contact with the environment to do something useful. If you think about it, manipulation is a big part of why robots are useful. Well, to manipulate the environment, the robot needs to make contact with it. Even locomotion requires making contact with the environment, and that's another big part of robotics. So contacts, of course, could be of different kinds. You could have soft contacts, or you could have rigid contacts. In reality, all contacts are soft. Okay, even when you're making contact with a piece of steel, it's still soft. So it means that you can have some deformation of the material. But for modeling, when a contact is sufficiently stiff, we actually assume that it is infinitely rigid, so that there is no deformation at all, because that makes the modeling actually much easier from a numerical viewpoint. And actually, most contacts that robots typically make are quite rigid. So if you make contact with a wall, yeah, there might be some deformation in the wall when you touch it, but it's so tiny that you don't even feel it. You cannot measure it. So as a matter of fact, it's better to model that as no deformation at all. So that's why here I'm focusing on rigid contacts, because they are much more common in practice than soft contacts. And also soft contacts are much easier to deal with than rigid contacts. So I prefer to explain you how to do the hard case. The easy case, well, it's easy. So let's discuss how we deal with rigid contacts. The problem with rigid contacts, what makes them hard, is that they constrain the motion. What do I mean by that? I mean that the moment you make contact with the wall, you can no longer freely move in space. Because if you try to move in the direction of the wall, well, you're not gonna to. There is a wall that is preventing you from moving in that direction. What you're gonna do instead is that you're gonna generate a force exerted on the wall, and the wall is gonna generate a force that is equal and opposite to the one you apply to it by Newton's law. So we need somehow to make the controller aware that there is this motion that it can no longer do, so that it doesn't try to do it. And we need to make the controller aware that there is a contact force that is generated if it pushes in that direction. So we need to modify the control problem quite a bit here. It's not as simple as switching from fully actuated to underactuated systems. Here we need some structural change to the problem. So let's start with the constraint. The constraint can be written down typically in this form. We have some function of the joint angles, or the robot configuration more in general, which remains constant. So this is a mathematical expression for saying the contact points don't move. And this is actually a simplification of reality. Because if I make contact with the wall there, well, it's true that my contact point, which is my fingertip in that case, is not gonna move, but it's not gonna move only as long as I don't break the contact. So if I push against the wall, then my contact point is not gonna move. That's accurate. But if I pull, then it is going to move, because the force is unilateral. I can only push, I cannot pull on the wall unless I'm glued. So this constraint here is simplifying the physics, meaning that it's saying that my contact points are glued to the environment. And so I can both push and pull on those. The reason why it's doing that is that if I wanted to model the real physics of unilateral contacts, I would no longer have a quadratic program. I would have an optimization problem that is much more complex. And I don't want that. So here I'm going to work with this like simplified contact model, which assumes that my contact points are basically glued to the wall. But then I'm going to take care of that assumption later when dealing with the contact force. So let's just assume for a moment that my contact points are indeed glued to the wall. This is accurate. But I cannot work directly with this constraint because my decision variables are q double dot and tau, and this instead is a function of q. So I need to do the same thing that we saw before, which is I need to take derivatives until I see q double dot appear. If I take the derivative once, I get the usual expression jq dot equals 0, which means contact point velocities are 0. If I take the derivative another time, I get this other expression, which we have already seen, jq double dot plus j dot q dot equals 0, which means physically that the contact point accelerations are 0. And this is an expression I can work with in my problem because it's a linear function of q double dot. So this is going to be a constraint that I add into my optimization problem to account for the fact that the rigid contact constrains the motion. This Jacobian, of course, is not necessarily the Jacobian of the end effector. It's going to be the Jacobian of this function here, which is going to be the end effector position only if my contact is at the end effector. If I'm making contact with my elbow, then it's going to be the Jacobian of the elbow, not of the end effector. Now we need to deal with the second aspect of having a contact, which is I have contact forces in the dynamics. So my dynamics needs to include the contact forces. Well, we saw when we did the review of robot dynamics that the contact forces enter inside the dynamics in this form. We have an extra term, which is J transpose F, whereas this J is actually the same J that I use here. It's a J corresponding to the contact points. I think it makes perfect sense. So my new optimization problem is this one. And the main differences are highlighted in yellow and blue. So I've added an extra constraint, which is jq double dot plus j dot q dot equals 0. That is telling my solver the contact points cannot move. And I have a new term in the dynamics, which is J transpose F, which represents my contact forces. I did something else. I included F into my decision variables. And that may seem weird. But if we reason a bit about it, it's not that weird. So the reason why I said it may feel weird is that you might think that the contact forces are not up to the solver to decide. They should be up to the environment to decide. Because it's the environment, after all, that is applying a force on the robot. So if the environment changes, the force is going to change, and the robot cannot decide what force is applied on it. However, under the assumption we are working with, which is that contacts are perfectly rigid and don't move, it's actually reasonable that it is the controller that decides how much force is applied. Because basically the force that is applied on the robots is equal and opposite to the force that the robot applies on the environment. And the force that the robot applies on the environment depends on the motor torques that the robot generates. So if I generate a higher torque, then I'm going to apply a higher force on the environment. If my torque is lower, then I'm going to apply a lower force on the environment. And everything works out perfectly. This is a crucial difference with respect to the case where the contact is soft. If the contact is soft, then the force that I feel at a given moment in time is fixed, because it depends only on the deformation of the contact, which depends on my position. And I cannot instantaneously change that. I need to modify my position to modify the deformation, and that in turn modifies the contact force. When it's rigid, instead, everything is instantaneous. If I apply more force, I get more force because there is no deformation. So if I apply 10 Newton on the environment, instantaneously I get 10 Newtons back. It's an approximation of reality because actually there is a deformation. But when the deformation is so tiny because the stiffness of the environment is so high, like a wall, then the time that passes between me applying 10 Newton and me getting back 10 Newton, well, I don't know exactly how much is that, but I guess it's well below 1 millisecond. So it's well below the control period of my controller. So it would be stupid to try to model that dynamics because it's so fast that's invisible to the controller's eyes. And so we work with this rigid contact assumption. So because of all of this, if I have a rigid contact model, I have to work with my contact forces as a decision variable of my problem. If instead I had a soft contact model, then I would need a sensor to measure the contact force. And the contact force here would be a constant quantity, and it wouldn't be a decision variable. So very different. But as I said before, soft contacts are very rare in practice. Most of the times in robotics, you have a rigid contact. So this is much more common. So we have a problem now that has more variables because we have the contact forces, which we didn't have before. It has more constraints because we needed to add these new contact constraints. And you can plug everything into a single constraint in matrix form using this expression here. Now, since you have the contact forces as a decision variable, you can add also inside the cost function any linear function of the contact forces. So if you have a force that you want to track, because maybe the robot is carrying out a task that requires to apply a specific force on the environment, like cleaning a table with a sponge, you want the robot to apply 10 Newtons on the table. You can do that by adding here a task on the contact force. And you can add also inequality constraints on the contact force, which we are going to discuss after the break because I see you're a bit tired. So let's stop here and I'll see you back at 9:40. So a very important constraint that we need to consider when dealing with contacts is the fact that contact forces are not free to move anywhere they want. Typically, they are bounded. Well, first of all, because we can only push on a unilateral contact, we cannot pull. And second, because tangential forces are also bounded by friction constraints. So friction allows you to apply only a certain amount of tangential force on a surface before you start slipping on it. Typically, when a robot makes a contact, you don't want the contact to slip. And so you want to consider that constraint. So friction cone constraints are typically represented in this form here. So the norm of the tangential force must be smaller than the friction coefficient, mu, which is typically a value between 0 and 1, times the square of the normal force. So the more you push on a contact, the higher tangential force you can apply. I think we all know that intuitively. And this is the model that typically people use for modeling that constraint. It's a simplified model, of course, but in robotics, it works pretty well. The problem with this model is that it's quadratic. And we know that if we want to use a QP as our optimization solver, well, we can only deal with linear inequality constraints. So what people do in practice is that they work with an approximation of this quadratic constraint. So this is a representation of the quadratic cone seen from above. If you look at a quadratic cone from above, well, you're going to see a circle. You can introduce a linear approximation. So we can approximate this circle, for instance, with a square, like this blue line here. If you want it to be more accurate, instead of a square, you can use like 6 sides. And of course, the higher the number of sides that you use, actually this is 7, I think. 1, 2, 3, 4, 5, 6, 7, yeah. It's 7 sides. The more sides you're gonna use for approximating the cone, well, the more accurate you're going to be, but you're paying the price by having a higher number of constraints, because each side here is gonna be one constraint in your problem. After you're done with your linear approximation, the constraint is going to look like that. It's going to be a matrix B times F less than or equal to 0. The matrix B is going to have as many rows as the sides you have in your polygonal approximation of the quadratic cone. So if you're using like a square, a 4-side pyramid, then B is going to have 4 rows. If instead you're going to go for like 7-side pyramids, you're going to have 7 rows in B. Of course, you should always use like an inner approximation, not an outer approximation, because by using an inner approximation, you're conservative. So you're sure that if you satisfy the inner constraint, you also satisfy the real constraint, which is the quadratic one. I always get phone calls during lessons, and I don't know how to disconnect my iPad from my iPhone so that I don't see them, but I'll figure it out eventually. So once you have this, well, you can just plug it as an extra constraint into your QP. And the advantage of this is that this actually takes care also of the fact that the solver is never going to ask for a force that pulls on the wall, that pulls on the contact, because this also accounts for the unilaterality of the contact force. So the normal component of the force is always going to be non-negative.
Sorry, but I didn't understood what the friction corner. Why were you?
Well, it's not a choice. I mean, when you make a contact with an environment, friction happens. Okay, so if I touch the wall there, I can push on it, but I can also apply tangential force. If I apply too much tangential force, then I start slipping. Okay, that's basically a limit coming from friction. So if I want to avoid slipping, I need to tell the solver that there is a limited amount of tangential force that can be applied on this wall. If I don't have that constraint, what can happen is that the robot actually thinks that he can apply infinite tangential force and think that it's just going to stick there, but that's not what's going to happen. So that you're going to have, this was a very bad idea, now I have a white hand. You're going to have a mismatch between the physics and what the solver thinks the robot can do. So ideally, you would like the two things to be as close as possible. And this also, to a certain extent, solves the problem that we are using this like simplified contact model that says that the contact point cannot move. Because this was very dangerous if used alone. Because if you just use this model, then the solver basically thinks that the robot can pull on the wall as if it was a bilateral contact. Like if it was a handle that the robot has grasped, where you can both push and pull. But when you're making a contact with like a wall, that's not a bilateral contact, it's a unilateral contact. And this is not modeling unilaterality. Luckily, we can re-include the unilaterality in the force inequality constraints. So this kind of fixes that problem for us. So now the solver knows that it cannot pull, that it can only push. So it's never going to ask for pulling on that contact, which means that the contact is never going to be broken, at least not on purpose by the solver. The limitation of this approach for dealing with contacts is that still we need to decide which contacts are going to be broken and which contacts are going to be maintained. So if we want the solver to break a contact, then you're not gonna do this, because this is actually preventing the contact from being broken. If you want the robot to maintain a contact, then you're going to do this. So this decision, make or break, it's up to the user. It's not automatically taken care by the solver. You need to use much more advanced techniques for taking care of this decision, which are actually subject of ongoing research. So the standard way is you basically, depending on the task you want the robot to perform, you decide if the contact needs to be maintained at this point, or if you want the robot to break the contact. If you want to break the contact, actually, you don't need to do anything. So since you want to break it, the contact force is going to be 0. You don't have any constraint. You're simply going to command the robot to move the end effector away from the environment. And that is going to break the contact, so you don't need to model the contact force and the contact constraints. So that's very simple. If instead you want to maintain a contact, then this is what you do. But you need to decide which action you want the robot to take. Okay, we have one last topic to cover, which is multitask control. So far, we have been focusing on the case where the robot has to perform one task. So tracking a trajectory, reaching a point, controlling the orientation of a camera. But in practice, very, very often you want the robot to do multiple things at the same time. Maybe they are not all equally important to you. There is one main task, it's a primary task, and then you might have another or maybe two other secondary tasks. Actually, we have already discussed this when discussing the problem of redundancy. When doing operational space control, we saw that if the robot is redundant with respect to the task, you have this null space and you can use this null space. Actually, you need to use this null space to stabilize the joint motion of the robot. Otherwise, it might just go nuts and diverge. Here, when you're doing QP-based control, you have exactly the same situation, but you have a much more flexible framework for dealing with multiple tasks. The way that you can do that in a very simple manner is to simply define a cost function for every task. So you use the same methodology that we have described for doing task space control. So instead of having a single function g, you can have a set of functions, g0, g1, g2, g3, how many you want. They're all going to have the same shape. They're all going to be least squares functions. And then in your cost function, you're simply going to take the summation of these functions, considering different weights for each of them. And you're going to give high weights to the functions corresponding to the primary task and smaller weights to the functions corresponding to secondary tasks. As simple as that. The reason why this works is that if you're summing up least square functions, what you're getting in the end is again another least square functions, which is needed if you want to maintain this least square program. You don't need to do anything regarding the constraints or the decision variables. They remain exactly the same as in the previous case. So you're just modifying the cost function by basically summing multiple cost functions together. The only extra challenge for you as a user of this framework is that now you have these extra parameters w, which you need to define. And you need to be a bit careful in how you define them. If you have only 2 or 3 tasks, that's typically very easy to define W's. You just set them like a couple of order of magnitudes apart. Like you have a W for the least important task, which is 1. Then for the task that is more important, you set it to 100. And then the other one is going to be 10,000. So you typically maintain the ratio between the weights constant. And typically you want it to be at least 100 or even better 1,000 if you really want like a strict separation between the tasks, or you don't want to make compromises between tasks of different importance. So the first task really needs to be achieved no matter what. And the second task needs only to be achieved if that's feasible under the constraint of achieving the first task, and so on and so forth. So you want a strict hierarchy between the tasks. Typically 3 orders of magnitude between the weights is enough to achieve that. If instead you have tasks that are like equally important or whose importance is pretty close, then you might have closer weights. So that's really a modeling choice, which is up to the user. And you typically tune them by trial and error. The situation becomes trickier if you start having more than 3 tasks. when you start having like 4, 5, 6 tasks, but that doesn't happen very often, luckily. Because in those cases, if you want to maintain like a 3 order of magnitude distance, for instance, and you have 5 tasks, it means that the ratio between the weight of the most important task and the least important task is going to be something like 10 to the power of 15. And that's too large. That's going to lead to numerical issues inside the solver. So inside, when you're doing numerical optimization, you never want to have numbers that are very large and numbers that are very small in the problem formulation. Ideally, you want to maintain all numbers roughly in the same order of magnitude. Of course, you can have a few order of magnitude of difference, but not too much. And 10 to the 15 is typically too much. So in that case, you need to do something else that is more complex if you really want to do that. But again, in practice, it doesn't happen that often unless you're working with a humanoid robot, which, I mean, for those robots, yeah, you might need to do like 5 different tasks at the same time to control it properly. But if you're dealing with simpler systems like manipulators or like wheeled robots, you're gonna deal with 2 or 3 tasks at most. Okay. So with this, we have concluded all the lecture on QP-based control. Since we still have almost half an hour, I wanted to add something on like the practical implementation of these control methods on real robots. So I'm going a bit off script with that. So a big assumption of all the control methods we have discussed so far is that our control input for the robots are the joint torques. Who has ever worked with a real manipulator? Okay, 1, 2, 2. How did you send commands to the robot?
With each pendant.
So what were the commands?
Like straightforward, simply moving task and small programs with the pitch pendant or.
So like you were controlling directly the position of the end effector.
Yeah.
Okay. What about you?
Torques and velocity.
Torques and velocities at the joint level.
Yeah, also end effector, like end effector coordinates.
Okay, so you were controlling at the same time.
No, not at the same time.
Okay, you could decide whether to control it at the end effector or at the joint with either velocities or torques.
Yeah, it was like a joint, velocities and torques, and the end effector position and velocities.
Okay, what was the robot?
Frank.
Okay, the Franca robot.
The one there.
The one that is downstairs here in the lab. Okay. Okay, that is a robot that is, I think, much more used in research labs than in industry. What robot were you controlling instead?
Exactly. I don't remember the model.
Okay, I've never seen it, so I don't know. But I guess it's more like an industrial robot.
That's a robot, and then that's the gift to my old school.
Okay, okay.
It was an older style.
An old style industrial robot. Yeah. Okay, so what I wanted to get at is that in the industry, most robot manipulators come with an end effector interface, so you can directly control the robots in Cartesian coordinates. So you don't need to implement all these control methods that we are working with. And even those that come with a joint interface, I mean, most of them have both. So you can also send joint commands. But the joint interface only allows you to send either position commands, so desired joint angles, or maybe velocity commands, so desired joint velocities. That's it. You cannot send desired joint torques. So you cannot directly implement these control methods. Now the question is why? Is this just a software issue? I mean, it's just a matter of changing the software so that you can send joint torque commands? No, it's not just a software issue. I mean, the reason why they do that is that they know that if they allowed you to send torque commands and you try to implement these control methods anyway, they wouldn't work well. And the main reason is that most industrial robots have very high joint friction, extremely high joint friction. And if you have extremely high joint friction, then it's pretty hard to implement these like so-called dynamic control methods that we have seen here. So let's write a couple of things down. Most industrial robots only allow for joint position or velocity commands. They have high joint friction hard to achieve torque control. Do you know why they have high joint friction?
For stability.
Oh no, it's not on purpose. It's not on purpose. It's a consequence. It's an undesired consequence of the mechanical design, let's say. They are heavy, but you could have a heavy robot without high joint friction. That's not impossible.
For the tolerances of the gearboxes.
Yeah.
So
yeah.
when they push, they have to be precise, and therefore there are also it has friction.
Yeah, I mean, again, it's not desired, the high joint friction. It's a consequence of the gearbox. So electric motors, they work well in low torque, high velocity regime. But in robotics, we need high torque, low velocities. So the way we do this switch basically is by introducing a gearbox, because the gearbox is allowing the motor to run very fast while the joint is much slower, and the motor produces little torque while the joint receives high torque. It acts as a multiplier for the torque and as a divider for the velocity. But this conversion comes with a cost, and the cost is that you introduce friction typically, especially if you want a high gear ratio in your gearbox. By high, I mean typically they are above 50. So you're multiplying the torque by a factor of 50, or actually you can go even up to 200 or 300 in some cases. So this introduces a lot of friction, and friction is what makes achieving torque control very hard, because it's very hard to model and it's very hard to compensate for. It's very hard to model because it's highly nonlinear. it depends on parameters that you don't observe, like temperature. So as the robot moves during the day, it heats up and the friction changes. So it would be very hard to have a good model for that change. And even if you had a perfect model, since friction is so nonlinear, it's actually discontinuous. Even if you have a perfect model, it's super hard to compensate for it. And I can say that because I've spent years working on that in my PhD and postdoc. So basically, if you have one of these robots with high gear ratios, you're going to have high joint friction, and it means you cannot really achieve torque control. It's not only a software issue, it's a mechanical issue. So you're going to need to work with joint position or joint velocity control. That's the only thing you can do if the mechanical design of the robot is not thought for doing torque control.
What if it doesn't work with
electric motors?
For example, with
hydraulic.
air.
Pneumatic.
Yeah.
Yeah, there are other kinds of actuators. Hydraulic and pneumatic are the two alternatives that come to mind. I know hydraulic much better because I've worked with it. So for hydraulic, I can tell you friction is even higher, but with hydraulic, typically hydraulic robots are equipped with a force sensor at the joints, and the actuators are so high performance that by using feedback control on this force sensor at the joint, you can achieve very high quality joint torque control. So with those robots, if they are properly equipped with force sensing at the joints and they have very high frequency joint control loop, you can achieve very high quality torque tracking. Pneumatic, I've never worked with them. They are much more rare in my experience in robotics. And the main reason is that they are very nonlinear actuators, and so they're very hard to model and control. That's the only thing I can tell. But electric motors are actually much more common, and they're actually eating up even that small fraction of the markets that were using hydraulic and pneumatic, because they're getting more and more efficient. And so you're going to see, I think, less and less other kind of actuators in robotics.
Less hydraulic.
Yeah.
Even with the bigger robots.
Yeah, at least for like intelligent robots. Then if you're talking about an excavator, yeah, that's going to remain hydraulic. But like robot manipulators or humanoids, this kind of more like intelligent advanced robots, I think they're switching more and more to electric. That's the trend in the last decade at least. So we have this problem that we have high joint friction, hard to achieve torque control. And then we can also write joint friction is mainly a consequence of high gear ratios. So roughly speaking, if you need to work with a robot, at least that's what I do, the first thing I try to figure out is the gear ratio, because that's immediately tells me, okay, am I going to be able to do torque control on this robot or not? If it's above 30, 50, it's going to be very hard to do joint torque control. If it's below that number, then most probably I'm going to be able to do it. Of course, there are other factors to consider, but my experience, that's the most important number you want to look at. Of course, you might have a combination of some joints that have a very high gear ratio and other joints that have a much smaller gear ratio. And in that case, you might have some joints where you can do torque control and others where you can't. And well, that's a bit tricky in terms of deciding what control strategy you want to implement there. So if you cannot do joint torque control, is everything we have seen useless? Not necessarily. You could still apply the control method that we have seen, but with a twist. So what can I do if I cannot send torque commands? You can do something very simple, which is you can compute the torque commands as if you were controlling a robot that can accept that. And then instead of sending the torque commands, you're going to compute the joint accelerations corresponding to those torque commands. You're going to integrate those joint accelerations to get joint velocities. And you're going to send the joint velocity commands to the robot. It's not going to be the same as sending torque commands, but you're still basically able to benefit from all the modeling that we have in our QP-based control. So you're going to be able to account for joint torque limits, joint velocity limits, friction cone constraints, contact constraints, everything that you can deal with when you're working at the dynamic level of the robot, even if your robot is only commanded in joint velocities. So what you can do is step 1, solve QP as usual to compute Z star. So that Z, if you remember, was the name of the optimization variables in my QP problem. And Z contains Q double dot star and tau star. Now, if your robot is torque controlled, you simply take tau star and you send it to the robot as your command. If it's not, then what you do is that you integrate Q double dot star. So your desired joint velocities are going to be the integral of these accelerations, of the optimal accelerations computed by your QP. And then you're going to send these joint velocity commands. It's every control loop. So if your control loop is 1 kilohertz, you integrate every milliseconds. So this is not going to be as accurate as having a robot which has torque control, because now there is an extra dynamics, which is the low-level controller of the robot that tries to track these velocities, which is not going to be perfect. It's going to introduce some delay. And so the real torque that are going to be generated by the motors is not going to be exactly equal to the torques that you have computed with your QP. But that's the best approximation you can hope for with such a robot. Okay. And this is actually not only working for the last kind of control methods that we have seen, so the QP-based control. The same you could also apply to the other method, like operational space control. There you have the disadvantage that the method only computes tau. So to get Q double dot corresponding to tau, you need to do some math, some extra computation. It's not very difficult once you have tau to compute Q double dot. You simply take the dynamics of the system. If you have tau, well, Q double dot is simply going to be M inverse times tau minus H. You need to do that extra bit of computation. And then you have it, and then you can integrate and send the joint velocity commands to the robot. So the main disadvantage of doing this is that the robot is still going to behave in a very stiff manner, as typical industrial manipulators do. Whereas if you have a torque control robot, it's going to be much softer, much more compliant. So if you have a torque control robot, you can push it, and the robot is going to allow you to push it, because it's not going to oppose that push with a high force. When you have instead one of these robots with high gear ratios, to overcome the joint friction, which is very high, the low-level controller uses a very high gain feedback. And very high gain feedback means very strong reactions to perturbation. So if you try to push an industrial manipulator while it's moving, you're not going to be able to move it. It's too strong. I mean, it's too strong, and it uses the power that it has to oppose disturbances. If instead you're working with a torque control robot like the Franca that you mentioned before, that one allows you to push it. Why is it good to have a robot that allows you to push it? Can you guess? Well, there are multiple reasons, but I think there is one that comes to mind immediately.
Maybe for security.
Yeah, for safety. Because maybe you didn't mean to push it, you just end up in the path of the robot by accident. If you have an industrial manipulator, if you are in the middle of its path, it's just going to crush you. Okay. So it's dangerous. That's why you don't see human operators in close proximity to an industrial manipulator in a factory floor. Instead, this novel, like more advanced robotic systems that allow for torque control, they apply much lower forces. And so even if you end up by mistake in the path of the robot, it's going to gently push on you, but it's not going to crush you. So it's much safer for human robots, not necessarily interaction, but even just sharing the same environment without the robot being inside a cage. It's much less dangerous. That's the first reason. There are also other reasons why it's better to have a torque control robot, which are actually very much connected to this control methodology that we have just described. So if I have a torque control robot, it means I can send torque commands, and I can make sure that these torque commands are compatible with all the constraints that we have included in our formulation. So they're compatible with the joint torque limits, the joint velocity limits, the motor current limits, the friction force constraints, the contact constraints. Everything is going to be coherent with that mathematical model. If instead I have joint velocity commands, then it's going to just approximate that using this method I told you. So you lose all the, say, guarantees for those constraints. Okay. So we have another 10 minutes together. I wanted to use them just to show you the solution to this exercise here. So this was the exercise. Proves that two controllers are almost equivalent. The first controller was this one here, which uses a compensation of the bias forces in joint space. And then the secondary task does not compensate for the bias forces at all, because here I don't have the compensation for H. And this is actually almost equivalent to compensating for the bias forces in Cartesian space. And then the secondary task also compensates for the bias forces in joint space. So the way I'm going to do it is that I'm going to work on this expression here. So I'm going to write tau equal J transpose lambda x double dot desired plus J transpose mu. But instead of writing mu, I'm going to take the definition of mu from above, which is this one. So mu is lambda J m inverse H minus J dot Q dot. So lambda J m inverse H minus J dot Q dot plus the null space and here I have m q double dot desired plus H. Okay, so I just rewritten the control law from above in a single line. The first term doesn't change. Now, this expression here, if you remember, that's what we called J transpose pseudo inverse, because it is a left pseudo inverse of the matrix J transpose. It's basically this matrix here. That's the same matrix. So I can write this as J transpose pseudo inverse H minus J transpose lambda J dot Q dot. And here, well, I have the first term. So this guy, I'm going to call it N for short. So N M Q double dot desired plus H minus J transpose pseudo inverse H. And now it's easy to see that these two terms are equal and opposite. And so I can simply cancel them. And what I'm left with is J transpose lambda x double dot desired minus J transpose lambda J dot Q dot plus H plus my null space times MQ double dot desired. But MQ double dot desired was basically tau 1. So this is MQ double dot desired. What I wanted to show is that this was almost equivalent to the control law from above, which was J transpose lambda x double dot desired plus H plus N Q double dot desired. And indeed, we can see that the only difference between these two controllers is this term here, which is why I said almost equivalent. But apart from that, they are exactly the same. So basically what we were able to show is that compensating the bias forces in Cartesian space and then compensating again the bias forces in joint space in the secondary task is actually equivalent to compensating directly the bias forces in joint space in the primary task. So these two compensations summed together compensate the bias forces totally in joint space. So actually, this is a much simpler way of getting this compensation. We don't need to go through this complex expression here. We can use this much simpler expression there. Any question? Good. On Friday, we're going to have the first lab session. So bring your own laptop and be sure that you have the software installed and working so that you can follow along. I'll see you on Friday.